So related to the last lecture where we looked at reactions of nucleophiles with imines, we could do something similar. It's important to keep this in the context of carbonyls mostly, but imines do have an important consequence here, and that's the cyanohydrin reaction. So in the cyanohydrin reaction, what you do is you take a cyano group, which is CN, or cyanide. So from cyanide, which is Cn minus, and then you add that to a carbonyl to get an alcohol, which is sort of implied by the suffix of the term hydrin, alcohol or OH. So cyanohydrin reaction. So all we're doing here is we're taking cyanide and letting cyanide be the nucleophile, adding to carbonyls. And we want to think about nucleophilic addition as adding to our resonance structure where we have charge separation, so we can clearly see which atom accepts the nucleophile. But in addition to that, we should also be aware that imines can also react with cyanide anions in important ways. Okay, so what we do is we take our carbonyl and we're going to add it to a cyanide salt, because you can't just take an anion by itself. We're going to follow that up with H plus workup, and we get to an interesting reaction where we technically form a new carbon-carbon bond, though this process sort of exists in an equilibrium. Okay, so there's the overall process. The product is right here. This is a cyanohydrin. Now, what we can do if we want to consider a mechanism for this reaction is first draw the resonance structure of our carbonyl that is so helpful. Because it's that resonance structure that allows us to see how our Cn minus adds to our molecule. Namely, we're going to have the negative attack the positive. Now, where did the Cn minus come from? Well, we're going to take KCN, and remember that if we have a main group metal like potassium, sodium, lithium, we can cross those out and replace them with a negative charge to give us, in this case, our cyanide nucleophile. Once we add those things together, we're going to get this intermediate, which then reacts with H plus to give us this structure here. And the H plus reacts because the oxygen picks off the H plus to give rise to the product. Now, it's important to note that nitriles are compounds with a C-CN bond. It's not always the case, but for the most part, these things are not toxic. But anyway, you'll hear this term quite a bit, nitriles, in the context of cyanide chemistry. Now, just to remind ourselves, the Cn is a carbon triple bonded to nitrogen, and these things usually arise from a Cn minus anion through some sort of reaction. Okay, so I show one example here where the cyanohydrin is an example of a nitrile. So nitrile is another term for compounds that have a carbon triple bonded to a nitrogen present in them. Now, it's important to note cyanide is highly toxic. You want to stay away from it. I mean, you want to be safe with it. Let's say it that way. Whereas the nitriles are mostly non-toxic. I mean, obviously we can certainly find some examples, but the toxicity effects of the carbon-nitrogen triple bond are gone when that negative charge is gone, because we can't adduct to the iron in hemoglobin and that sort of thing and suffocate ourselves, okay? So that is sort of the cyanohydrin reaction. Now, there's some important nitrile chemistry that makes this reaction super relevant. So some useful nitrile chemistry. is that if you take a nitrile, so let's have some R bonded to, and I'm just going to rewrite it so I can see my carbon triple bonded to nitrogen, just so I can take stock of everything. It turns out that if you add, if you add water to this with acid or base, pretty flexible in terms of the conditions. Usually we have to have some sort of heat to drive this over a thermodynamic barrier, or excuse me, a high barrier for the reaction to occur. But what we get is a product where we have a carboxylic acid. And then if we're balancing this, it looks like we need to make some NH3, and I'm still not balanced here. Now I'm balanced. Okay, now I'm balanced. All right, so we have to have a couple waters coming, which makes sense. We have two oxygens in the product. But with acid or base, we can convert this nitrile to a carboxylic acid. Okay, now that's pretty interesting because what that lends itself to is a process called the Strecker reaction. I'm going to make a new page just so I can do it, just so I don't have to do it in a second here. Okay, so that's relevant to the Strecker reaction. So in the Strecker reaction, what we're going to do is a series of events where we first take a carbonyl, and then in step 1, we're going to add NH3. In step 2, we're going to add HCN, and then in step 3, we're going to add H2O, and with H plus or some sort of pH that's not super neutral. Okay, now why would we want to do that? Well, if we do all of this, it turns out we can get, I'm going to make this an R group right here. If we do all of this, it turns out that we can get a molecule that looks like this. Okay, now this molecule is an alpha amino acid. And so here we have sort of biology. We have biology from abiotic biology or before life biology. So we've got some origin of life stuff. We've got some origin of life stuff to consider here. Now I can't say for sure it's origin of life stuff, but origin of the biomolecules, I'm not saying it's not origin of life. I'm just trying to give you guys facts. Origin of biomolecules, check, definitely. That's a definitely yes. The Strecker reaction was used to generate a lot of very useful biomolecules. Because if we look here, why is this all of a sudden origin of life? Well, we've got NH3, HCN, and H2O were abundant in prebiotic Earth. So they were abundant in prebiotic Earth in various mechanisms. This is kind of like the Miller-Urey reaction we talked about in Organic 1, where we zap some lightning with some stuff floating around and we get amino acids. This is one of those processes that occurs. Amino acids was one of the types of biomolecules. We get a lot of precursors to sugars and that sort of thing too. Okay, so how does this work? Let's go through the mechanism of the Strecker reaction really quick. And this is going to be a brief mechanism. I'm not going to cover every single curly arrow event. I'm mostly going to show you the outline of how this works. It's more of a, it's not so much of a mechanism as it is a how the Strecker reaction works. So in the Strecker reaction, what we start with is a reaction where hopefully we're getting more and more comfortable with each time I remind you of, and that's the reaction of a carbonyl with a nitrogen species. Now this nitrogen species has an NH2, so we can do a condensation reaction to generate water. However, the thing coming along for the ride with our nitrogen atom is simply another hydrogen atom. And as a result, the imine product is going to be this structure here. Now what that means is that when we, so this is step 1, we're going to generate water. In the subsequent step, in step 2, we're going to take that exact same imine intermediate and react it with HCN. HCN is a pretty strong acid, so you're going to get some equilibrium where you can have Cn minus and our H plus. Now this is kind of useful for us because here we have our H plus for our workup step along with Cn minus, which is required for the cyanohydrin reaction. Here I'm going to show the negative charge adding to the carbonyl, and I'm just going to push the electrons up. I could have alternatively drawn that resonance structure that shows the carbon with a positive charge. That's pretty useful, but I'm just trying to show as much as I can on the screen here. So I'm just not really skipping that step. I'm just showing an arrow to accommodate for that step. Okay, anyway, we can add to the nitrogen, and then the nitrogen is going to pick off the H plus that's floating around from our HCN starting material to give us, now I'm sure people know how basic or acidic we were in the early atmosphere, but if this is step 2, then step 3, what we're going to do is react our Cn with H2O, and we could have 2 of them, and that's going to give rise to our final product after we convert the nitrile to a carboxylic acid, and we have an amino acid. Okay, so either H plus or OH minus, acid or base, will allow for 2 water molecules to go in and add to the nitrile to make a carboxylic acid. This then gives rise to amino acids, which are the building blocks of proteins, an important building block to life as we know it. So an important step in getting to where we are right now in terms of the complexity of our biological systems involve first generating those building blocks. Now, some of you may remember from the quote Space Dinosaurs lecture that processes like this without some sort of something chiral present are going to generate a racemic mixture. We've generated a stereocenter, so what's called the alpha position of this amino acid. We've generated that stereocenter, but we haven't controlled it. We haven't controlled whether it's a wedge or a dash, so we get a racemic mixture. Generating stereocenters is not hard for the universe to do. Generating them as a single enantiomer is very difficult to do. Biology is really good at it. It'd be super cool to know how biology got to be so good at it. Anyway, that'll do it for this lecture on cyanohydrins. We'll pick up with more reactions of carbonyls next time.